Hi, welcome back. So in this section, we're going to talk about Wi-Fi security, or at least a little bit about Wi-Fi security. So as an introduction, last time we just talked about 802.11 in general and some of the different flavors and the control frames. In this section, we're going to talk about a number of security protocols that are available for use with 802.11. And we're also going to talk about a number of security issues that exist in 802.11. So we get both. Things that 802.11 does well for security and things it does bad for security. So first, let's talk about encryption. Encryption of Wi-Fi traffic is optional. It's not required by the 802.11 standard. And without encryption, which is the way a lot of access points are configured, especially public ones, all packets are sent in the clear because they're not encrypted. And that means that anyone within radio range can listen to those packets and decode them and look at them. In fact, if you boot up Kali on your machine and you use the right tools, you can reconfigure your wireless card to listen to all packets on a given Wi-Fi channel. So you could see all the traffic that anyone around you on that channel is sending. And this is called monitor mode for your card. So that's kind of the level of scariness. You just boot your machine up in an alternative Linux distribution, and now you can see all of the Wi-Fi traffic anyone is sending. Okay, so let's describe this scenario a little bit. So if we look here, we see that we have two stations. One, normal, let's say that's you. We have the access point. And then we're going to have a malicious attacker over here. And you can tell he's malicious because he has horns. And his goal is to listen to your traffic. Now, what we'd like to think happens is that I put together a packet and I send it to the access point, and the access point goes ahead and forwards it on to maybe the internet or wherever it needs to go. And I'm happy because my traffic went from me to the access point, and the attacker's sad because it didn't go to him. But that's not what really happens, sadly. The reality is that when I transmit my packet, it doesn't go directly to the access point. Instead, I'm broadcasting it wirelessly. And radio transmissions go out in this every direction sort of idea. And so anyone within range actually receives a copy of my packet. It's just a matter of whether or not they actually do something useful with it. So the access point gets a copy and forwards it onto the internet, just like you would expect. But in this scenario, the attacker also gets a copy because he's also within range. And so that's the issue, is if your packets aren't encrypted and anyone within range can see them, then that could be a problem for security. And now our attacker is very happy because he can actually get your packets. Okay, so what are the options for encryption in 802.11? Well, there's 4 different encryption modes. Open, which means there is no encryption. WEP, which is a type of encryption. WPA, and WPA2, both also other ways that encryption is configured. So let's talk through these 4 one at a time. So the first is open. Open, just very simply, no encryption is used. Obviously, there's not security here or protection for the confidentiality of the data being transmitted, but open is also very, very commonly used in public places or large public Wi-Fi networks because it's easy to connect to. You open up your laptop, there's an open network, you double-click on it, you connect, done. Life is easy. But whenever you do that, you just have to know that there's no encryption being used, and anyone around you could potentially see the traffic that you're generating. The next type of encryption mode for 802.11 is called WEP, and WEP stands for Wired Equivalent Privacy. And from the name, you can tell that the goal when they designed it is that they want the confidentiality of your packets to be about as good as it would be if you were using a wired network. And the reason for that is because that's kind of what people expect. If you're connected to a wired network, I don't expect the person next to me to be able to just simply see my packets. Now, WEP has 2 different modes, a weaker and a stronger encryption key. So you're either using a 40-bit or a 104-bit encryption key. And as you look at those 2 numbers, especially the 40-bit should be very worrying. That's an awfully small number for an encryption key. And 104-bit might be okay, and we'll talk more about that in another lecture. So in WEP, all clients use the same key. So the encryption key is configured at the access point, and any client who wants to connect has to know that 40 or 104-bit key. And they need to enter it, usually in hexadecimal. it was not the most user-friendly security standard. Someone comes over to your house, you say, oh yeah, you can use my Wi-Fi. My password is 084ABF7C. Just kind of this nightmare. Entering those things was a real pain, and it was not very user-friendly. WEP uses a stream cipher, specifically the RC4 stream cipher for the encryption. And you may remember that the way a stream cipher works is that you use the key and typically some sort of initial vector in order to produce a key stream. And then that key stream is exclusive word with the plain text in order to produce a ciphertext. And that's what happens here. In WEP, we have RC4 as the stream cipher. A key mixed with an initial vector is used to generate some key stream, and that key stream is exclusive word with your data packet before we transmit it wirelessly. WEP is very, very broken. There's a lot of issues with it. We're going to have a whole lecture about it in the future. So don't use it ever for anything anymore. But it's kind of fun because we'll play around with it, and hopefully we'll have a chance to break WEP as like an activity. WPA, it was kind of a follow-up to WEP. So WEP was very badly broken, and so the follow-up to it was called Wi-Fi Protected Access, WPA. WPA uses a 256-bit key. So that's a significantly bigger key than the 40-bit or even the 104-bit WEP. And a very important change is that clients don't all use the same key. So the actual key used for encryption differs from every client, between every client and access point. So if you're connected to the same access point as me, we'll use a different encryption key to encrypt our traffic. With WEP, we would be using the same encryption key. WPA still uses RC4, but they changed the name to TKIP, just for fun. I think it's Temporal Key Integrity Protection. I don't remember. But they just call it TKIP. And there's two different modes for WPA. The first is pre-shared key, which is basically you enter a password. In fact, this is probably the way your access point at home is configured. There's probably a pre-shared key that, so you turn on the laptop, you connect for the first time, and it asks you for the password to the access point, and you type it in, and then it connects. The other mode, which is more rarely used, and you might not have seen this one, is called enterprise mode. And enterprise mode allows more complex authentication. Typically, it's used to authenticate with a username and password. So QU doesn't have that now, but they're hoping to add it in the future. Enterprise mode, meaning that when you connect to the Wi-Fi for the first time, it'll have you enter your QU username and password to connect. Okay, so WPA2 was a follow-up to WPA, where there was two main goals. One was to fully standardize the security procedure, but the other was to switch from using RC4 to AES as the cipher. And this is a good change. Now, well, they use AES, but they call it CCMP. So WPA used RC4 and calls it TKIP. WPA2 uses AES and calls it CCMP. Don't ask me why they decided to give existing ciphers new names, but they did. WPA only used RC4/TKIP so that old hardware would stay compatible, because what they were dealing with was a situation where WEP was badly broken, and they needed a new standard to provide better security, but all of the hardware in existence was designed around using RC4 as its encryption cipher. So they made WPA to also use RC4 so that they could reuse the same hardware, the same cryptographic hardware that was already out there. WPA2 is kind of where they went back and said, now let's do it right. And so they switched to AES. In general, you want to use WPA2 whenever possible. There's no reason not to. So I want to add a side note here on WPA versus WPA2. The difference between the two has gotten very blurred, mostly by marketing people. There really isn't that much of a difference between the two. I mean, there's the difference in ciphers, but marketing people got involved and decided they wanted to try and market like, well, we support WPA2 instead of just WPA. And the whole thing became a horrible nightmare. And to this day, every time I teach the class, people say, what's the difference between WPA and WPA2? And every time I say, I'm not exactly sure. I think it's the ciphers. And then every year I go to Google and I check. But it's never any better. Every year, you try it. I mean, try Googling. Say, just go to Google and type in what's the difference between WPA and WPA2. And you get all of these weird forum posts of people trying to figure it out, and no one really seems sure. So in the end, there's not much of a distinction, but the important distinction I want to make sure you understand is that you can use RC4 or you can use AES, and it's always better to use AES. Okay, so based on the stuff we've seen about 802.11 in general and about these security features, let's talk through some security problems and simple attacks that are based on them. Okay, so the first thing, I'll call this the forced disassociation attack. And the observation I'm making is that control frames aren't authenticated in any way, so there's no integrity for them. Well, if there's no integrity for them, then if I receive a control frame, how do I know it's actually from the person that it claims to be from? I don't. It could be from anyone in wireless range who sent a packet claiming to be from anybody else. There's no way to authenticate it. It's like getting a letter in the mail that has a return address on it, but you have no way to know if the return address is correct. You don't know. There's no way to tell. So anyone in range can forge control frames claiming to be from anyone else. That's an important thing to keep in mind. Well, if that's the case, and a disassociation frame is used to disconnect someone from the network, well, then a simple attack would be to just forge disassociation frames and send them to lots of clients on the network. And then those clients will end up being disconnected from the network because they're forcefully disassociated. So they get disassociated, they try to reconnect, and it just keeps going and going and going. For a class project one year when I was still in university, I built a simple app that sent these forged disassociation frames to clients on the network, and it was surprisingly effective at just forcing someone's computer completely off the wireless and cutting off their connectivity. And there was nothing you could do to prevent it because there's no authentication on the frames. There's no checking of the integrity. So I would send a disassociation frame to another station claiming to be from the access point, but there was no way to know that it wasn't. So it's a very effective attack. And in fact, I don't know what it is, but there's probably some simple tool on Kali that can do that without any trouble. So another type of attack is just simple traffic sniffing. I mean, I've mentioned that anything you send is transmitted wirelessly. Well, if encryption isn't used, if it's an open network, then that means all traffic is sent unencrypted. And so the simple attack is you put your card in monitor mode and you just listen to all the traffic and you look for interesting things. In fact, there's tools to do this, that just flip a card into monitor mode and watch for anything that they might see that would be interesting. Passwords, emails, instant messages, etc., etc. Now, I want to make a note here that even if the wireless network is unencrypted, some of the traffic that you're generating to the network may still be encrypted. Because, for example, if you use HTTPS when connecting to a website, well, encryption is occurring at the application level. It's not occurring at the wireless traffic level, but at the application level, it's all being encrypted. And more now, websites and mobile applications and things like that are using secure communication. So this idea of I'll just listen to unencrypted wireless traffic and I'll find passwords is really not that effective anymore because the individual application protocols are being run over encrypted tunnels already. And so it's not as interesting as maybe it was at one time in the past, but it's still a potentially interesting type of attack. So a third type of attack is based on WEP. And so you may remember that I mentioned that when you use WEP, all clients use the same encryption key. And that's an important thing to know because then if all clients use the same encryption key, then if you know the key, you can use it to decrypt other people's traffic because they're encrypting their traffic with the same key that you are. So if you're a valid user on a WEP network and you know the key, you could decrypt anybody else on the network's traffic. So the simple attack is you listen and decrypt traffic from others that are on the same network that you are because you're all using the same key. And that's probably not good. I mean, it's not as bad as being able to listen to anybody's traffic on any open network, but just because someone has the WEP key to a network shouldn't necessarily mean that they can see all the traffic by any user on that network. So this isn't great either. So WEP has other problems, and I'll call this number 4 loosely WEP encryption problems. WEP uses short keys, 40-bit or 104-bit. 40-bit is ridiculously short. 104-bit is maybe a little bit better, but still not good enough because of some other issues. And another problem is that it reuses initial vectors when it encrypts packets. So if two packets are encrypted with the same key and the same initial vector, then they were encrypted with the same key stream. And that's a problem, because you may remember that I mentioned when we talked about stream ciphers and one-time pads, which stream ciphers are meant to simulate, that it's important to never reuse the same key stream. Well, WEP effectively does reuse key stream, and this opens up problems for it. Additionally, just to add to it, RC4 also has some mathematical problems. So WEP's got a lot of things going against it. First, it used short keys, which was a design mistake. Then it reuses initial vectors, which was an implementation mistake. And then the algorithm that it uses has mathematical problems, which is a fundamental mistake. So it's got three different types of security issues, all wrapped up in one security protocol called WEP. So a simple attack is you just break the WEP key. And it's disturbingly easy. In fact, if you have the right tools, you can do it in less than 5 minutes. You can see a network that's encrypted with WEP, and you can break the key and know what it is in less than 5 minutes. It's disturbing, and it's just because of WEP it's just got 3 significant errors in its build, and so it's really easy to break. So another issue, WEP's really easy to break. WPA is not weak in this, or WPA2 is not weak in the same way that WEP is. Like the cryptography is okay, and the design decisions are much better. But WPA in pre-shared key mode, where you have like a password basically, lets the user pick a password for their access point. Well, when users get to pick passwords, they tend to pick bad passwords. And that's not good. And so one simple attack is you could try to brute force the WPA password. And there are tools designed for just that, brute forcing the WPA password. This also works against WPA2 because the protocols really aren't different. Yeah, so you can brute force the WPA password based on a dictionary attack or things like that. So that means that if users choose a bad password to try and secure their network, that an attacker could potentially find it, and potentially find it very quickly if it's a really bad password. Okay, so let's summarize. There are 4 security modes available when we're talking about encryption for wireless: open, which is no encryption; WEP, WPA, and WPA2. Unencrypted traffic can be sniffed and easily picked up by anybody in radio range. WEP traffic can be sniffed if you know the key. And the WPA passphrases can potentially be brute forced if they're weak. So that's kind of our summary of today.